So our next speaker is Oli Jones from Berlin. They will be talking about cyclic splittings of Artin groups. Over to you, Oli.
Yeah, thank you very much, Gemma, for the introduction and invitation to speak here. So today I want to talk about cyclic splittings of Artin groups and then mention an application to the isomorphism problem in the second half. All of this talk is based on recent joint work with Giorgio Mangioni and Giovanni Sartori. So let's start with the definition of an Artin group. Today, for us, the most convenient definition is going to be based on a presentation. So we're going to start with our finite simplicial graph and label all of the edges with integers at least 2. And then we're going to build a presentation where we have one generator for each vertex. So you can see down here I have an example, and we've got A, B, C, D as generators, and one relation for each edge, which is going to be some kind of generalized braid relation. So it's going to be of the form, for an edge ST, it's going to be of the form STS, etc., equals TST, etc., where the length on both sides is the number labeling that edge. So if you take your label 2, then you have a commutation relation. If you take your label 3, you have a braid relation, and you have some kind of generalized braid relation for higher labels. So this class generalizes braid groups and right-angled Artin groups, which are just when you have all your labels being 2. But almost any question that you can ask in complete generality about Artin groups is hard. And today we're going to see result towards one of these hard problems, like a partial result. Definition we're going to use again and again is a parabolic subgroup. So this is a class of subgroups generated by a subset of the generators. So for instance, I could take the subgroup generated by C, B, and D, and then it's isomorphic to the Artin group on the induced subgraph of those generators. So for that example, I'd have generators B, C, D, and relations B, C, B equals CBC, and BD, BD equals DB, DB. So it's just exactly the Artin group there looks like it is. That's a theorem of Van der Leck from the 80s, I believe. So yeah, the next thing is to introduce this problem that we're kind of working towards. So it's an unfortunate fact of life that given an Artin group just up to isomorphism, you can't talk about the defining graph because you can have non-isomorphic defining graphs as labeled graphs, which give rise to isomorphic Artin groups. So the isomorphism problem, which is a specialization of Den's isomorphism problem, is asking if we can algorithmically decide, given two defining graphs, whether they give rise to isomorphic Artin groups or not. So here I think it's useful to have an example of two different graphs that give rise to isomorphic groups. So we've got this gamma and lambda. And if you see what we've done, we've taken this edge AB and kind of slid it along the edge BC that was labeled by 3. And anytime you have an odd edge which separates the graph, then you can always slide part of the stuff on one side over to the other side. And we call this move a twist. And that gives rise to isomorphic Artin groups. Now, conjecturally, the only thing you can do to get isomorphic Artin groups from the same graph is do twist moves. So that's sliding along an odd edge on some higher dimensional generalization. So really, when you're doing isomorphism problem stuff, the thing you're trying to do is find invariants which can distinguish different graphs which don't differ by twist moves and say that they give rise to non-isomorphic Artin groups. And that's the direction that we're eventually aiming for today. Cool. The next thing that I want to talk about is the other word from the title, which is splittings. So I think this will be familiar to many people here, but if not, don't worry, everything that you need to know is on this slide. But yeah, we say a group splits over an isomorphism type of class of subgroups, but in this case, it will always be over Z if it acts non-trivially on a simplicial tree and with edge stabilizers isomorphic to Z if it's a Z splitting. By Basset theory, this kind of geometric characterization is equivalent to an algebraic thing, which is that you can express your group as a HNN extension or an amalgamated product, and with Z as the group you're amalgamating over, for example, if it's a Z splitting. I should have said this non-trivially here just means without a global fixed point. Of course, any group acts with a global fixed point on a tree. Okay, so really you can think of whichever of these definitions you prefer during the talk. Often it's convenient to go back and forth between them when you're working with this stuff. And now we're going to have an example of a splitting for an Artin group, and in fact a class of splittings called visual splittings. Yeah, anytime you have a graph like this gamma, which has a separating vertex, like this one that I've labeled by A, then we can decompose it into two induced subgraphs, which intersect only over this separating vertex A. And this gives a corresponding amalgamated product decomposition, which you can get just from the presentation, of A gamma 1 amalgamated with A gamma 2, where these are the parabolics that we talked about, amalgamated over exactly the subgroup that it looks like, which is the subgroup generated by A. And by this correspondence, we should also have an action on a tree, which I've notated here in graph of groups notation. If you're not familiar with that, you should just think this is an edge in the tree, which is a fundamental domain, and the stabilizers of the two vertices are A gamma 1 and A gamma 2 respectively, and the edge stabilizer is the subgroup generated by A, which of course is isomorphic to Z. And it should at least be reassuring, if you've not seen this before, that the intersection between A gamma 1 and A gamma 2 is the subgroup generated by A, and if you fix both endpoints of an edge, then you should fix the edge. So this kind of makes sense, but given this data, you can develop out into a full action on a tree. Cool, so the first main theorem that I want to talk about today is saying that in fact, all splittings of an Artin group over Z are one of these visual splittings like we saw on the last slide, more or less. So specifically, if we take any Artin group where the defining graph is connected, so this is actually equivalent to the Artin group being freely indecomposable, and so it's not that big of a restriction, because if you want to split your group, like you should look at one-ended things. Like first you should split over the trivial group if you can, and only when you've done that should you split over Z. So this is a kind of reasonable assumption in this context. And we ask that it has at least 3 vertices. This is because 2 generated Artin groups do split over Z in a kind of well understood way. But there's no separating vertex. So yeah, further statement, at least 3 vertices. Then the Artin group splits over Z exactly if there's a separating vertex. So we can do a visual splitting like we saw on the last slide. Cool. So this result is a generalization of a result by Clay from 2014 for right-angled Artin groups, which has exactly the same statement. And our proof is also a generalization of his. And I don't want to go into the details of the proof today, but the quick summary is that you're going to use the action on a tree, assume there's no separating vertex, and use cycles in the graph in order to build stabilizers which are bigger than Z, which contradicts the assumption that you had a Z splitting. Okay, so that's the splittings of Artin groups, and now we want to start thinking about the isomorphism problem. So there's an immediate corollary as our kind of warm-up. Something we can immediately say about the isomorphism problem is, suppose we have 2 Artin groups, A gamma and A lambda, and A gamma has a separating vertex. Then A gamma splits over Z, which is a property only of the isomorphism type, right? It just says there is an action. It doesn't say anything about the graph. So it's also true that A lambda splits over Z. But then by the theorem, A lambda also has a separating vertex. So immediately, if we have 2 graphs, one of which has a separating vertex and the other of which doesn't, we can say that the Artin groups aren't isomorphic to each other, which maybe we couldn't before. So that's nice, but we'd like to say better, we'd like to distinguish more graphs, and for that, we're going to need some kind of heavier machinery, which I'm now going to introduce. Let me know if there are any questions, by the way, or you should speak probably, because I can't see everyone. Okay, cool. So the main technical tool we're going to be using from here on out is JSJ decompositions, which originate in three-dimensional topology. So yeah, originally this was a thing for three manifolds introduced by Giorgio, Schalen, and Johansson, so JSJ. So the idea is that if you have a three manifold, then you can cut along certain tori to leave pieces that you can't cut further, or at least can't cut further in a canonical way. I don't want to worry about this too much today, but the picture to have in mind maybe is one dimension lower. Think about a surface. You can cut a surface along a circle in many different ways, but there's no canonical one to choose. And that's the kind of thing you might be left with. Of course, in three dimensions. Okay, so this was a useful tool for studying three manifolds. And if you think about what's happening when we do this on the level of fundamental groups, because we're cutting along tori, then by Van Kampen theorem, this is the same as like taking amalgamated product along z squared. So the idea now was to push this tool that had been used for three manifolds to groups by mimicking what's happening to the fundamental group of the three manifold for other groups without the underlying topology. So this idea has been developed by many authors, going back, as you can see, to almost 30 years. Most prominently is probably Seller's work for hyperbolic groups, and indeed Seller's JSJ decompositions for hyperbolic groups were important for solving the isomorphism problem in that class. So there is some history of JSJ decompositions being used for isomorphism problems. Okay, so now I want to state the definition of JSJs, and you'll notice this is a definition. The actual definition of a JSJ decomposition is a bit more general than this, but today all of our JSJs will arise in this way. So I thought I'd specialize the definition to what we'll see, because the general definition is a bit more technical, and yeah, there's no point looking at that, but just to disclaim. Okay, so we say that a splitting, which is nothing but an action of a group on a tree, is a cyclic JSJ splitting if for every other cyclic splitting, so every other action of G on T, some tree T prime with cyclic edge stabilizers, all of the groups that are elliptic in T are elliptic in T prime as well, where elliptic is just fixing a point. So it's some kind of maximal splitting. It says we can't decompose any further because these vertex stabilizers don't split, so we can't have more stuff acting loxodromically than we already do somehow. These things always exist for finitely presented groups. This kind of follows from Dunwoodie's accessibility theorem and is written down in Girardel and Levitt in a very general way. But that proof is not explicit, and what we're going to see in a moment is an explicit JSJ decomposition that we can then use to say more for Artin groups. And this other thing, which is going to come up in a moment, is that JSJs are not usually unique. So there's no the JSJ decomposition for a group. Cool, JSJs for Artin groups. So I want to make a definition that a big chunk parabolic subgroup of an Artin group with a specific graph gamma, I guess, is a maximal parabolic subgroup without separating vertices. So if you look at this, I guess it should be connected. If you look at this blue square here, then there's no separating vertex, but as soon as we made it any bigger, if it was connected, this would be a separating vertex. Given that definition, you can probably convince yourself that for any simplicial graph, we can decompose it into a union of big chunks, as I have this one here, which is color-coded. And once we do that, then we can produce the JSJ just by taking visual splittings exactly like we saw a few slides ago. So again, you can think of this as a fundamental domain for the action in the tree. We have a vertex for each big chunk, whose stabilizer is the corresponding big chunk parabolic subgroup. And we also here introduce these dummy vertices, which are going to have stabilizer equal to the subgroup generated by the separating vertex, so stabilizer Z. And then we just add edges corresponding to inclusions of separating vertices into big chunks. Now, this is a JSJ decomposition because any of these big chunk parabolic subgroups doesn't split over Z, but that means if you think about the action of this Artin group on any tree, then this subgroup then restrict the action to the action of this subgroup, then it must have a global fixed point, because otherwise this would split over Z, but doesn't have a separating vertex. But that's exactly the definition we just saw of JSJ decompositions, that all of the elliptic subgroups must fix a point in all Z splittings. There was a small lie in that argument, which was this yellow edge here is 2 generated, and our theorem was only for 3 generated or more Artin groups. Like I said, these 2 generated Artin groups do split over Z, but they do so in a kind of understood way, so you can show that no such splitting can extend to a splitting of the whole Artin group. So this does end up being a JSJ, just with slightly more argument. Things are also more complicated if you have leaves on your graph, so because then you have 2 generated big chunks, which aren't kind of pinned at both ends. And the JSJ looks a bit different, so for today we're not having leaves, but the same thing is still true. You still have a JSJ. Cool. Yeah, next I want to come back to this non-uniqueness of JSJs that I mentioned. So here we have on the left 2 isomorphic Artin groups, and we know they're isomorphic because we've just slid this blue square down the yellow edge, which has an odd label, 3. And this is one of these twist moves that I mentioned that is known to give rise to isomorphic Artin groups. So these are the isomorphic groups, but if we do the JSJ procedure that I just described, we get different JSJs. And this shows you what I said, that JSJs aren't unique. They are related to each other if you have 2 different ones for the same group in an understood way, but you can't do what you might want to have done and say, okay, I take my 2 Artin groups, I take the JSJs for both of them, and if they're different, then the Artin groups were different. Such an argument can't work because even for isomorphic Artin groups, we can have different JSJs. And so we have to work a bit harder than this, but I think it's a good example to have in mind. And we have to use this relation between JSJs, which is this lemma here, which is essentially due to Forrester. So suppose you have 2 splittings of a group G, which are both JSJ splittings, cyclic JSJ splittings. The cyclic isn't load bearing here. Then any group that acts elliptically on the first tree T also acts elliptically on the tree T prime, any subgroup. And this is great for us because we controlled exactly what our elliptic things were. They were the big chunk parabolic subgroups in our JSJs. So this is very quickly giving us our main theorem for the isomorphism problem, which says, suppose we have 2 isomorphic Artin groups, then the big chunk parabolics of A gamma match up with the big chunk parabolics of A lambda. Like exactly, counting multiplicity and everything. You can really show that you have like the isomorphism might not send the big chunks to the big chunks. That's a bit too much to hope for, but there will be, although it will be true up to conjugacy. But if you take the multi-set of isomorphism types on the left and on the right, you know that they match up exactly. So that's the statement. And now I promised that this would help us distinguish some more Artin groups. So Let's see some examples of what we can do. So if we take our A gamma 1 and A gamma 2, as I've taken here on the left, then if we look at the big chunks, which are just the triangle and the square in both cases, then on the left we have this 3, 3, 3, 4 square, and on the right we have this 3, 3, 3, 3 square. The Artin groups on these graphs are not isomorphic to each other. This is by a result of Nicola Vascu. But that result is for large type Artin groups, which means no twos, so it doesn't extend to the whole, it doesn't allow us to distinguish these two Artin groups. But now, by the theorem here, we know that the big chunks don't match up isomorphically to each other on the left and the right, which means that these two Artin groups can't be isomorphic, which is good because they don't differ by one of these twist moves. So we didn't think they were isomorphic. So that's a positive thing we can do, but there's still things left that we'd like to distinguish and can't. So if we look at this A gamma 2 and A gamma 3, what we've essentially done here is slid this 3, 3, 3, 3 square along the edge labeled by 4. And this is sliding along an even edge, not an odd edge. So conjecturally, these two Artin groups should not be isomorphic. But our main theorem can't distinguish these two things from each other because the isomorphism types of the big chunks are the same on both sides. We have the 3, 3, 3, 3 square and the 2, 4, 4 triangle. So a kind of next step that it would be good to be able to do, which we can do in some kind of, with some more restriction on the isomorphism, but not completely in general, is to use the JSJ in a more refined way and be able to distinguish not just what's there, but also how it's attached to each other to hopefully distinguish two Artin groups like this. But of course, if you're attempting such a thing, you have to be careful because the way things are attached together is not kind of completely rigid. So you'll have to allow some flexibility. Yeah, I think that's everything I wanted to say. So thank you for your attention. And if there's any questions.
Thanks very much, Oli. Let's thank our speaker. Does anyone have any questions for Oli? Everyone's being very shy. I'll maybe get the ball rolling with, it's probably too vague a question, but going back to, I think it was slide 5, you had kind of like your main theorem. I was just curious as to, so you say the result was extending results of clay for right-angled Artin groups. And I'm just curious kind of how different, or was there new techniques you had to use to generalize to, you know, a much larger class of Artin groups compared to RAAG? Like it seems like a very big jump from RAAGs to Artin groups with at least 3 vertices.
Yeah, yeah, it does seem like a big jump, and of course we did have to do something more, like Clay's proof doesn't work verbatim. But you can, the thing that you're using here is that so 2 generated Artin groups have a center. So if you think about an edge in an Artin group, then you can kind of think about subdividing it by introducing the center in the middle. And then the like consecutive things should commute with each other. And conjecturally you okay, not quite, but you're seeing like theories of commuting things which almost look like a RAAG in some conjecturally precise sense inside your Artin group, and we're kind of using these embedded chains of commuting things. They don't quite make RAAGs, of course, but yeah, that's kind of the idea behind how the generalization works. Yeah, we made other changes to, there were a few times Clay used things that aren't known for all Artin groups. Of course, there are many such things, so we had to circumnavigate that, but the strategy really is Clay's, even though the details had to change.
Okay, great. Thanks. I appreciate that was a very vague question, so well done. Any further questions for Oli?
I
Okay.
guess another thing I could,
Oh, sorry.
sorry,
Go on. Oh, no, on you
another
go.
thing I could say in answer to your question, Gemma, is for RAAGs, since Clay's result, there's more general things that are understood. For instance, something kind of similar for when RAGs split over abelian groups, and more general things beyond that, which we don't yet know how to recover for Artin groups. So there is, as you'd kind of morally expect, there are more things you can do for RAGs than for Artin groups for now. But that's kind of, I think there's
Right.
interesting questions in that direction as well.
Okay, nice. So there's maybe scope to do even more, perhaps.
Yeah.
Okay, cool. Nice. Okay, if there's no other questions, let's thank Oli again.